Hello everyone. Today I'm going to talk about longer stay less priority flows length approximation used in information agnostic traffic scheduling in data center networks. My name is Mohammad Shahid Iqbal and I'm a PhD student at National Yang Wing Chiao University, and my advisor is Professor Chen Chen. As we know that the data center, that there are different cloud applications running in the data center network like social networking and retail recommendation. And these type of applications are very demanding in latency requirement. A tiny delay can directly affect the performance and degrades the user experience. So the goal of the cloud application or the data center network is to minimize the flow completion time. We have multiple proposals in order to do so, but the optimal one on which everyone agrees is the shortest job first. So the existing solutions are of two types: information-aware solutions and information-agnostic solutions. The information-aware solutions like PDQ, pFabric, and PACE were presented like in 2012. The problem with these solutions is like they require the flow size information in advance to mimic the shortest job first. And as we know that acquiring flow size information in many scenarios like HTTP chunk transfer, or in case of database query response, we cannot acquire the flow size information in advance. So these information aware solutions are like they are not feasible to implement in the real environment. And there comes then information agnostic solutions like PIAS and DIAS. And the PIAS involves both end host and the switch for the scheduling. What happens at the end host, the PIS, it counts the number of bytes sent at the end host and adds a priority tag to every packet. So the switch uses the added priority tag and places the packet to the queues accordingly. So the constraints with this PIS is like they need to install a kernel application at the end host to count the sending bytes, which is not feasible like in 100,000 end host data center. And the counting also takes some processing power, which can also introduce an additional delay. And there is a constraint in the PIS. It can misjudge some special long flows as a short flows. LSLP uses active time of flows to schedule them in strict priority queues by leveraging the p-flows, which is programmable nature. Instead of scheduling a single flow, we combine a group of flows together which arrive during the same time slot, and then we assign the priorities to the group. For example, here we have the three different time slots: T1, T2, and T3, and the new flows coming A1, A, B, and C at time slot T1. So all the new flows are assigned to the highest priority queue, and at the beginning of the next time interval, the packets of the existing flows A, B, and C will be placed in the second highest priority queue, and the new flows arriving during time slot T2 will be assigned to the highest priority queue. So the packet D1 is the beginning of a new flow, so it is assigned to the highest priority queue, and the packets B3, B4, and A2 are assigned to the second highest priority queue. Similarly, at the beginning of time slot T3, the E1 is the new flow, E is the new flow, so the packet E1 is assigned to the highest priority queue. The packet B5 is from an existing flow, so during the previous time interval it was placed in the second highest priority Q2. Now it will be demoted further to the one lower priority level in Q3. So F1 is the new flow assigned to the highest priority queue, and D2 packet is from an existing flow which arrived during T2, and so it will be placed in the second highest priority queue. We have implemented LSLP with a small test bed, like we have one receiver and 6 senders, and in the middle we have a P4 switch. So the receiver sends request according to the distribution, and then the senders receive the request and response accordingly. We generate 10,000 requests, and then we receive the response of the 10,000 flows from the sender. So we receive like this much of flows. We see that the flow completion time of the short flows 99% flow completion time, and medium flows flow completion time, and the high and the large flows flow completion time. And we also show that overall average flow completion time of different loads, like 50% load, 60% load, 70%, 80% load, and we compare the TCP data center, TCP PIS, and our implementation, and we see that overall average flow completion time for website workload and for the data mining workload, they are similar in all the techniques. But if we go for a flow completion time, we split our flow completion time results into different flow sizes, and basically our goal is to minimize the flow completion time for the short flow, so we only discuss this one. Here we see that our implementation have a little higher flow completion time than the PIS, and 99 percentile flow completion time as well. This was expected because the PIS implement a strict counter at the end host, while we approximate the flow completion time, while we approximate the active time at the switch.